So first one was univariate, second one was pair plotting. Now the third one is we begin to get into regression, polynomial regression, right? Now, let's make it a little clear. All right, so let's load the files. You know how to do it. Just open up linear regression. Just open up your Jupyter notebook, go and find your file here, linear regression. Linear regression is supposed to be done with an external data set, which looks like this. Let me grab my pen. Now you don't know what this means, right? We have to now understand what this mean actually. There is the label. We go and check the code where you're okay. What is this data set? Boston housing data set. Okay, so some housing details of the area of Boston is made available to us for us to understand. This data has a little information which is much more different from what we saw earlier. Okay, in the California data set. This is a little different. See this. CRIM is per capita crime rate by town. Okay, so per capita crime rate by towns in the Boston area. Okay, so it is there. ZN, proportion of residential land zones for lots over 25,000 square feet. Proportion of residential land owned for lots over 25,000 square feet. Okay. How many of the total respect to the land zoned for lots over 25,000 square feet for each of the township? Okay, so that is this value. Proportion of residential land zone for lots over 25,000 square feet. Means all the over 25,000 square feet housings. That value, the proportion of that with respect to the total area of that township. That is this value. And we don't know why this value is important. And you might wonder like why this is more important. So that is all part of feature engineering. They realize that, hey, if we can have proportions, then we can get a better model, right? So what is INDES? Proportion of non-retail business acres per town. If a town has around 1 lakh square feet, how much of it is non-retail? Then something called Charles River dummy variable, 1 if tracks bounds river, 0 otherwise. Okay, Charles River dummy variable is something as a geomap, some geolocation. It's more about that mapping this one. So there is one term, Charles River dummy variable, 1 if track bounds the river. Okay, if it is bounded by a river, if it is 1, otherwise 0. Then NOx is nitric oxide concentration. RM is average number of rooms per dwelling. Again, you get all these basic housing properties. Proportion of owner occupied units built before 1940. Again, another proportion. Weighted distance to 5 Boston employment centers. Weighted distance is you can have any kind of weights there. Any kind of weights over there. You know, in that, what is weighted distance? What is weighted distance? Let's just get my in entire machine learning, you will constantly see one concept again and again. What is that? Weighted. Okay, why weighted is important? Let me just more often than not, you'll be. Yes, sir. Priya Arundhati ji has said, even if VTU has given list of programs, can you provide the proper ordering? Yeah, I provide the proper ordering. Don't worry about it. Because some things have to be taught after certain things. Oh, don't worry about it. Correlation by Mahesh. Something I don't understand. Mahesh Kini M sir's bit on correlation. I don't know whether it was a question or whether it is an uh, you know, agreement. You can give more insight, Mahesh Kiniji. Was that question about correlation? Was it like you want to know more about it, or you are telling me something? Please give more details so that I can address it. Now, what is the weighted distance? Okay, suppose you are, let's say there is VTU. Okay, want to do a weighted distance to VTU since to 5 Boston employment centers, right? So let's say we do a weight. Now, how do you say? If I want to do where is VTU? It's in Belgaum, correct? So if I were to do data set of Belgaum itself, okay, township of Belgaum, then I will have towns in Belgaum, okay, some town called V1, V2, V3, and I will say then I will recognize 5 important companies, MNCs, which are very important for us. And let's say these companies are your Infosys, CS, Wipro, let's say Accenture. Also, we can have Intel. Intel hires a lot of people. So, okay, 1, 2, 3, 4. Now, how far is B1 away from Infosys? Weighted distance. So, if this is very far, we have to sum up all this and take the average. So, we give a new feature saying B1's value with respect to the employment generation is a new number, which is a weighted distance of how far B1 is from all of this. So we can just look at so when I get numbers like this, they are very near. What happens? It is near, right? If they are very, very near, then the weighted distance, yes. So we can now, when we look at the table, we can say if the B1's value is very low, it means it is very near to the employment center. If it is very near to the employment center, the value of property in the town of Belgaum where B1 is there, that value may increase. That they understood. Why did they create to choose this? Because that value may increase. That's why this feature is there. And you must appreciate this. We are in 20 minutes already. Even if you started at 9:15, we are already 20 minutes into and we are still understanding the data set only. Okay, so all of us must appreciate to get the complete knowledge transfer, we'll have to have patience. But my duty, I will not say I'm going to make machine learning easy for you. I'm going to make machine learning exciting, because this excitement is going to push you to bear with all the maths and all the uncomfortable symbols that you're looking at. This excitement is the one which is going to carry forward you with all the hindrances or the walls that you have in your mind. We will have to break through using your enthusiasm, excitement, and that feeling that you're learning something new. So that's what I'm trying to get you here to do. And I would appreciate if you can do the same thing for your students. I think then you'll empower them to do self-learning on their own. And with ChatGPT everywhere, world is beautiful. Anyway, so you got the point. So this is how index of accessibility to radial highways. Then you realize like a RAD is a new concept which may affect the price. Then crime rate by town may affect the price. See, somebody wanted to predict the pricing of the houses in Boston. Now the question was, what will affect the pricing of Boston area houses? Then they realized, okay, crime rate could be something, because everybody will look like, if the crime rate is down, they'll all have high demand for that area. Then proportion of residential land zones owned by 25,000 square feet, big, because proportion of residential land owned over 25,000 square feet means what? More industries. Proportion of non-retail business acres per town is more. This is a new the index where you see that, okay, non-retail business acres per town means there is more growth of, there's more farming done here, because non-retail business acres. And then you have this, it is closer to the river, fish, maybe accessibility to good food, good seafood. Nitric oxide concentration, health. Average number of rooms per dwelling, population. Population also should not be too much, right? So see, these concepts, these are all feature. This is what feature engineering is. You just got a lot of data from the housing department, and then you derived all this data. And then there is full value property tax rate. Index of accessibility. These are all new indexes that you have seen. Then there is PT ratio, pupil teacher ratio by town. Right? And then there is some BK, where B is the proportion of black resident by town. Then there is one more value, LStat, percentage of the lower status of population. Median value of owner occupied homes in thousands. All this data you are looking at. We have to have appreciation of, okay, what are we looking at here? Okay, so making sense? Now you're comfortable with what data you're looking at, the indexes, what these numbers mean. As data analysts and scientists and ML engineers, we have to correct. Anita is right. And weights given to data point based on a distance from other data points. Yes, Survesh is also correct. Anita is also correct. Topic discussed again. Acha. So Mr. Mahesh said, okay, we also discussed correlation between. Correct, right. Right. So with this, let me delete this. Let's go a little deeper into the code. Then we do data.head. We load the data. We load the data directly to .pd.read CSV. One thing is true. See, all of this you're always going to look at. Okay, all of this you're always going to look at. And I also thought today I wanted to tell you something. I wanted to make something very clear. Is everyone here? Around 99 people are here. Fine, but when they watch the video, they'll understand. I wanted to break down something for you. Okay. See, let me break down the way a code looks. Okay. Always this general pattern will be observed in that code, in that ML code. One is one second. Okay, machine learning model, is this model, first of all. Okay, it is given. You are not rewriting this entire model. This model is there. It's called model, whatever the name is, dot thing. Understanding? This model dot something will always be there. What does this model dot something need? This model dot something needs what as input? From here you think this model dot input will need, there are two versions to it. If it is a supervised learning, you need X and Y. So this X and Y will go here. If it is unsupervised learning, you will just need a X. And this X can be a full data frame. All of it can be X. It will understand this is X1, X2, X3, X4, X5. It will understand the model. It is built like that. You don't have to break your head on this. You just have to look at where is the model and what am I going to feed here. Now you see. Next problem state, next general problem. So unsupervised, why you understand, can anyone tell me why unsupervised only has X? Because there is no, in supervised, there is no. Yes, absolutely. Unlabeled data, no target, no labels. Labels, no, see, labels will be there. Why labels won't be there? Label will be there. You may not use the label. You think like there is no label, then suddenly if there is a label and you want to do clustering. So see, this is labeled data now. This is all labeled. So I'm saying, okay, if you mean that labeling is about differentiating between feature and target, then you are right. Okay. So there is no differentiation between features and targets because we ourselves don't know what the target is. That's why we are doing unsupervised. That we are simply choosing, hey, today let's do unsupervised, like having the like with coffee code and a tea code, and that's not the way. The reason for unsupervised, because you don't know which one is target. Which one is supposed to be the target, we don't know. Right? That's when we do unsupervised. So when you're doing unsupervised, this model, if it is an unsupervised model, it won't take two values. It will say, just give me this unsupervised and some other parameters which is related to the clustering. Okay. Now you understood this. This is one part. So you understand that the code has to give you this provision. So all of this will go in libraries. And mostly you'll find these libraries either the NumPy package or the skitlearn package. Okay. Most of it are here. What it does, because this scikit-learn, the outfit. Okay. After you build the model, what else is there? Model evaluation. For this model, you have to do what? Train and test. So tell me how many, if you have to now, we don't know that which class a data point belongs to. Yeah, correct. No train only. No train. Correct. Correct. Output will not be exactly. Okay, we'll come to that. Everybody will have different answers, but the feel of it you will know. Fine. So I can bear with that. I can train and test. So you appreciate a model will always have an API opening where you put in the input. Then that model should give you the ability to input the data. That model should also give you the ability to the API for the model, not the model. The model is just what it builds for you. Okay. But the model's API should be able to give you the facility to automatically structure the data into train and test. Then after the model is built, you have to evaluate the model in terms of its accuracy. And there are many metrics for accuracy. Okay, this is how time goes away. I had 4 algorithms today, but definitely, but it's okay, right? Tell me how many people are okay with the patient approach, so that we are not trying to just finish the syllabus. We will take time. We will finish everything, but we'll take time to get there. Correct. Super. All right. So look at this. Look at, if you want to just write down, you have pen and paper and put everything in here, then I think you may want to do that. But what I'll do is I'll also snip this and send it to this one also. Your libraries like NumPy and scikit-learn, all of them are supposed to give you this. What else? See, there's one more issue. From here, let me just. X and Y, your data is a table. is an external. I'm sorry, my handwriting isn't really that good, but please bear with it. Data is an external table, and we need the ability to manipulate the data, feed the right structures into the API, correct? This one, who will give you the ability? This ability is given to you again by Pandas data. Your manipulation of separation of X and Y, differentiation between train and test, and all of this, Pandas library will give you. Then general EDA, what is that? Exploratory data analysis. Pandas will give you. Before even you start building a model, you should explore the data. Otherwise, you don't know which model will work. This EDA is the situation where you'll realize there is no target which is actually making sense. We ourselves don't know. After doing all the exploratory data analysis, we came to know that there is nothing that we can infer from the description. What do we do now? So we ask the machine only to do some smart trick so that it will give us more insight into the description of the data, what it means, correct? So once this unsupervised is done, we come to know where the clusterings are happening. Then we choose a target and then we try to build a model, correct? So see, that's why you have these things. So it's but natural that when you start, you are going to look at the imports because you need all this. So there, every time you see, there will be imports. Then you will use pandas because you are going to import everything. You need pandas to manipulate. You need NumPy for numerical calculation. You need the matplotlib to see the plot because that is inference. You need a higher level of a plotting ability to see different kinds of pictures because your matplotlib is only as good as just simple, plots, right? But these kind of analysis, which requires higher dimensional graphical abilities that SNS has. Okay, so SNS and were same, but my SNS is built over on Seaborn, right? Built over this. So we got that under Seaborn. We are importing Seaborn as SNS. So it's just the object of the class type Seaborn. So that's how you should see it. This is also an object of the class pandas. And this object will come with a lot of methods. And that method is called the API. Okay. All of them is packed in a package you can call module. And then you see it gets sklearn model.selection import train test split. And all of you understand what train test split is. What is the difference between model evaluation and model performance? If you study the model's performance, you can say that I have evaluated the model. That's what it means. It's the same, but the model performance is an adverb. Model evaluation is both are about the model. Yeah. So model evaluation and model performance are almost the same, according to me. I mean, somebody might surprise me saying that, hey, there is a subtle difference between model evaluation and model performance. I'm sorry if I don't know that, I don't have much knowledge about that. But for me, if I'm doing model evaluation, I'm studying the model's performance. Okay, I hope it makes sense. So even if you think generally, what else it can be? Why warnings are important? Is it necessary to write? Why warnings important? Is it necessary to write? Warning. Okay. Sometimes what happens, right? Sometimes this Python people, they keep it is a constant effort. It's a constant effort to make the system better. Now I may be running which Python, I don't know. I did not update Python from a long time. So my version of Python will be somewhere lower than what is currently running. And suddenly I might require a particular library a particular library where I need a library which is already working for the updated system. Then there will be some warnings. That warnings will stop my flow. So simply I've just put it. You can remove this also and work on it. What happens? These are all the technical nuances, which is like the implementation details. You can use, it will work. If it works without you using this, then all your libraries and including your Python is updated. But some of the codes that we are running requires old version. So in my system, I'm not updated to any of the newer versions. Okay, because some older libraries that we've written, that will also be used by us, right? So I don't want to simply keep upgrading. But so what I'll do is I'll just ignore the warning if at all there is warning. And warning is not error. Okay, warning is something like, warning is something like, for let's say you have a syntax. You have a syntax to call for, let's say, for each X in something. Now suddenly the Python, new updated Python says you can't write it like this anymore. Now you have to write for each. But I don't know this. My Python is not, I've updated the Python, but I'm still using this format. So Python is the interpreter, because Python is an interpreted language, not a compiled language. What it means is, first, this entire thing gets interpreted. Then it goes for compilation. Okay. So in the interpretation only, it will interpret that this person is supposed to write like this, but he has written the old code. It says, okay, fine, but don't keep doing this again. It will give a warning saying, see, this is also deprecated, but still I'll allow you to use it because anyway, I can interpret it. And eventually, I'm telling you, this whole thing will go. That is what AI is going to do. Okay, AI is going to be so smart that if you simply talk, that's what we are doing with ChatGPT, isn't it now? You just talk to ChatGPT and get the whole code done. But how you talk, what you're talking, and especially when you're teaching, to get an implementation code in the industry, it is very easy. Okay, when you're teaching, it is very difficult. For you also, I appreciate the kind of drudgery that you will go through every day, because the average student is also very intelligent now. Simply get some doubts, this and that, and they'll simply, for the sake of it, they're going to just have this one, right, the interest, and to get that. So where in that time, you have to appreciate the fact that there are certain things which are always beyond this one. Why to import trace split? Okay, any supervisor in desert has to divide 80% or 70% training side, 20% 30% testing. So split is necessary. Okay, right. So Anita Ji has answered. Very good, thank you. But tell me, how many of you, I want to know, how many of you really want me to explain train test and what it does and everything? Some people, I heard that yesterday, I read a lot of feedback. For some people, it's the first time they're handling ML. So you can give me a thumbs up if you want to. If you want me, I would like to see how many thumbs up goes up for train test. Please, everyone, please just involve yourself. I want to see, like, what, 109 people are there. I just saw only 15 thumbs up. Still only 20%. At least the normal distribution says 66% is normal. It's natural. At least I would like to see 60 people's thumbs up. So okay, everybody just have, okay, fine. Let me address that also. Okay, what is train test? So pretty simple. But yeah, you will be able to appreciate it once you understand. Train test. For training and testing, I have to teach another step called people and population. Okay, just give me 2 minutes. Okay, I'll just take this water break, and when I'm back, I will. But now, what you should do while I'm gone, just for 2-3 minutes, or do some research. Go open ChatGPT on the side and try to understand what is a sample and what is a population. You know it already, but just refresh it. Be back in 3 minutes, just 3 to 4 minutes. It's best that I actually tell you what sample and population is, and then tell you about a model, and then I'll tell you why training tests are required. Sample and population. Okay. The way it works is, let's say you want to just a second. Okay, so let's assume that we have a Bangalore population. Okay, Bangalore population. In Bangalore population, we are going to do an experiment saying we'll collect age, we'll collect their experience, and we want to predict their salary. So what you do, look at the exercise. You're going to go on a bus starting from Electronic City and coming towards Majestic. Take all the age, you take their experience. We'll also record their salary. Now, this, whatever you have collected, the main data. Don't you think that whatever you actually have collected here is only a sample of the real population? There is no way you will collect all the people's data. It is not possible. That is why there is something called sample statistics. Whatever the sample is, whatever is the inference you make on the sample, what is the inference that you make using the sample, will it get applied to population also? What means, if I randomly now go from a randomly pick up somebody new, some new person here whose age is 35, whose experience is around 8 years, and this person's data we got it from suddenly somewhere from, you know, the person was traveling from BTM to Port. Some person was there, we got their data. Can we predict its salary, their salary? Predicted it, fine. We got one number. The model took 35 and 8 and it gave us a number. How confident are you that this number will actually signify this on the population? Because this person came from the population. The people in the sample were all target, the feature 1, feature 2. But the new prediction here, how confident are you this will actually be true? Because this, nobody is there. Nobody is there to tell you that this is the right thing. This is all a prediction only. Nobody can tell you whether your prediction is right unless you surprise him and say, you actually go and check the verify that document or ask them, hey, you're certified, I am guessing this much. Is it true? Then he say yes or no. Correct? So to be able to do that, although you have samples, so collect a large amount of sample. Okay? We collect a large amount of sample. So we collect a large amount of sample in our you can sample is a subset of population, sample is the entire data set. I can understand. I can appreciate that, whatever you said here in the chat. Anita ji, yes, right? So what I understand, ma'am, that you're saying, but I would like you to appreciate the difference that you can never collect the entire in statistics, you can say that, but in machine learning, see, this is actually the sample. You're looking at is the sample. This sample is the one which will go into the model to get built, right? What are we going to do in the model? We're going to build the algebraic relationship between these two features and the target. That algebra is the model. Okay. So we'll do today. We'll do the same exercise with linear regression. We'll understand what it is. Now, model what it is doing. In this, you will separate 80% of the data and 20% of it. So let's suppose I have A. Like I'll just give some number. I'll just give some symbols. Okay. Right. So you have different combinations of this, red, blue, and green, and you can have a lot of become something else. Totally different. Okay. So these values are saying when there is red and blue, it becomes green, and then there is red and some other color, red and yellow will become purple. Okay, this is your pattern. So it has to understand that a combination of something is giving you something. It will intertwine and it will do. But when you build the model, you use 80% of the data, train the model. So that relationship is built using the training. Now, once the training set is done, so you always see this train X and train Y. Then you have, this is the testing model. This is a testing sample or the testing percentage of data. Let's say you have test and you have test Y. To build the model on the training sample, you get a prediction API. So this prediction API was built using train X, Y. The model is ready for you. So you want to do something called model.predict. What are you going to give? If you want to predict some value, you will give a particular value from your testing sample. And what you will give? This is test Y, you already know. Okay, you're not going to feed the test here. Here in training, you give both because you want the relationship to be established. Testing, you will give only X. Give only the X value because the output should be Y. But when you split like this, you are in the testing sample, which X you will give test X. Okay, test X value. Suppose we have built a model. Suppose let's say there are 10,000 points above this. We've already built the model, and these are the only two examples. Okay, so we will give X, which is red and blue. What it will should be supposed to predict green. If this red comma blue gives you green, and then your red comma yellow gives you green again. So what is the accuracy of the model? 50%, because 50% true. Because we know this is not supposed to be green because test data we know, right? It's supposed to be compare. To compare only we do 80-20. Okay. So everything is stitched already in the libraries. You don't have to really worry about that. Everything is already. The difference between testing and validation. To test so that you can validate. Model evaluation, model validation, model testing. If you go and check the synonyms for what different, but if you think about it, no, think about English word validation, testing, evaluation, model performance. Everything is about how good the model is. Okay, so there are many metrics. I'll send you a video on different metrics of. Somebody remind me in the group that I'll send you a video of different metrics for a model. Okay, but is it making sense? Should I repeat? Making sense? 1. If you want me to repeat, type 0. . Of course, even if there is 1 0, I'll have to repeat. I mean, let me quickly come back. You have certain data. You have to split that data. This like this. Okay, say which one can we? So this data, let's look at this section. So this radius, texture, perimeter, area. Only this data. Okay, we are only going to be focused on this data. So with this data, with this data, I am going to do what? 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's do some kind of a split here. We will randomly split this. So we are going to make this as training, 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 train. Remaining is testing, 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 testing. Okay. So in training, you see, in our training sample, we have in the training sample, we have this, 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 this. In fact, we can make another one training. I would try to this. I can make this also training. Okay. So we have this and this 1, 2, and 3 to test. We build the model. Now we build the model using all this. Okay. The circular ones. Model is built using this. Test it on this. Why I'm testing on this? Because I already know that for these, and this value, the diagnosis is malignant for this breast cancer survey data. Okay. But next time when my model gives you this, I'll feed into my model these values. That model is not supposed to tell me whether M or B. But if it ends up telling me B, then out of 3 samples that I was testing, one is already wrong, which means already only 2 remaining. If all are wrong, then what happens? It will be 0% accurate. Okay. So what I'm trying to tell you is your ML model consumes all the training data with both the dimension X and Y, and this X can be of multi-dimension on its own, because this whole thing, you see this one, this line, this whole line, and this whole line here, right? And this one, everything is going to go as a data frame of X. Then we say the target is this variable here, M, right? And say the model is built. Once the model is ready, we try to do predict on it, and we send the testing sample, because otherwise what happens? If you don't send a test data, it will be like this. You're all professors and in the teaching line, so you'll understand, you'll appreciate this thought process. Suppose there's a kid goes to your class, okay, and in the class you are teaching this kid first time, okay. So you've taught him how to do 2 plus 2, it becomes 4. You've taught him how to do 2 plus 6, it becomes 8. And you've taught him how to do 2 plus 10, because it becomes 12. Okay. Now, suppose this student is now supposed to attend the test. We are going to give a test to the student. In the exam, which problem will you ask? Ask what is 2 plus 2, or are you going to ask what is 2 plus 5? Which one? Or 2? You will 2, right? 2 is better, right? Because at least you know that whether the person has understood the concept of addition. Otherwise, if you just ask 2 plus 2, we'll just memorize it and put 4. It shouldn't happen. Nice. What Satyanarayana has said is a very interesting, analogy. Actually, yeah, I can actually appreciate that analogy by Satyanarayana. It's nice. But anyway, coming back to the screen here. So, do you want to create a test? So this one came from where? Training data. The training data will be very different. Now you want to see how your model works on the training data. So you can if you test the student using a sample in the testing data, it is called testing accuracy. The accuracy that you got when you sent the same data that you used to build the model. If you send the same data for testing that you used to build the model, then obviously your accuracy will be high. If you use a data which is away and most likely to appear in the population, whose data you don't have at all. If it works, and if this training data accuracy, this is getting closer to 90% or 92%, you have built a beautiful model. It is 90% right on training data, but because the training data was never used to build the model. This is a great success when your model starts performing well. Training data, right? So that's the train test split that I was talking about. Why you have to split? You have to split because when you split, you know the features. In training data also, this target will be there. In testing data also, the target will be there. But we will take the training data and we are going to build the model. Model is now supposed to be ready to give out the prediction, but we know already a training data table where we already know the prediction. Now we are asking the model. See, I know from training data, I know some samples, some sample has a target. Yes, no, yes, no, yes. Okay. Some sample has this. Now I split this and I know I'll build the model on this. Next time I know I want to, if I give you this, if you can predict N, then it is fantastic. Okay. And when it predicts both N and Y correctly, then we get everything right. If you're training, because you know under training data, you know that this sample is no and this sample is yes. So when you put this one into the model, and if that model predicts exactly, right, exactly, then it is 100% accurate. And this model was built. This is a good diagram. I accidentally drew a very good diagram here. See, this one is built, but this is training. So I'm going to write the training test. In data, this is testing. So model is built and model will now, in fact, this is the model for prediction, and you will get the result. So making sense? Now shall we into some linear regression? A thumbs up if I hope all the people who said 0, I hope they got some clarity now. Moving on. Okay, thank you. So let's just go and I think I would like to open up my boards. See. This is probably the most simplest linear regression. This is not a part of it. This is part of when we teach. Here we teach like this. So let's not get bogged down by the code. Code is very simple. I want to just see, make sure that you see the code that is going to be developed. Okay, so age, salary. We're going to do simple linear regression. For 31, you have 32, you have 10. 35, you had. For 30, you have 16. For 25, you have 8. That's it. Okay, that's all. The graphs comes up. Of course, I told you, unless you put it in a reference system, you can't predict. This is X, this is Y. Which one should be X here? X is the independent variable, Y is the dependent. That's why you'll always see in linear regression, the simple linear regression, you are looking at this equation, Y is equal to MX. It's the simplest relationship that can be built between X and Y. It says X gets multiplied by a weight added by a bias. So if I give you, it says, if I give you 31, can you multiply with the weight and what should you add to 31 so that I can get 21? Are you understanding what is the equation? What we are trying to build? We are calling it as curve fitting. Okay, that is your linear. All prediction is curve fitting on. So just look at this. We can start from 0. And I'll say 5, 10, 15, 20, 25, 30, 35, 5, 10, 20, 30. Attention to this, huh? Age 31, salary 21. This is salary. This is age. We want to predict the salary based on age. That's why this goes as dependent variable, because we want to build a model where salary depends on age. Whether it depends or not is not our concern. That somebody will say, hey, how can salary depend on age? Yeah, correct. That is not our concern. Our concern is only the label and the number. You are trying to build a model. Whether the model is the wrong way to approach, that is not a Python or your mathematics doesn't care. It doesn't understand whether it's like a vehicle. If you are going in the wrong direction, it is not a driver's, it's not the vehicle's problem, it's your problem, correct? But we want to make salary dependent on age, and we want a function which tells me what is the dependence. And if you are going to do this both, where you see this x-axis is also metric data, which is moving, continuously moving, and y-axis is also continuously moving, then it is called a regression problem. If you had, instead of salary, if I say salary slab, right? Are you in the salary slab A where it is 4.2, whatever, 0 to 4 lakhs, then 4 to 8 in salary class B, then something else, right? So you have C and D. Now you have millions of data, only A, B, C, D are repeating. Now this becomes a logistic regression, which is not there in your syllabus. According to the ML here, it's not there in your ML syllabus. But when moving numbers are trained to either belong to a certain class, so it becomes a classification. It's not regression anymore. Okay. So you use, usually if there are only two variables, you use logistic regression. If there are too many, you use decision trees. We use Naive classifier. If it's really too many, you use PCA. That is dimensionality reduction. You reduce the dimensions. Right? Everything is there in your ML lab. You're going to learn all of it. Don't worry about it. So, doubt so far here? Anything that you are not able to follow? Premise is correct. Anything that is not, you guys think that anything that I've not explained in this figure here? Thank you. Thank you. When you people send some comments and all, no, it really gives me this one, feeling that we can go ahead. Now let's just go and plot it. Just go and plot. Where is for 31, 21? For 31, you have 31. Okay. Next is 22, 10. 22 and 10. Next is 35, 15. Where is 35? 35 is here. This person got 15. Next is 30, 16. Where is 30 here? And where is 16 around here? What is going to look like this? Okay. Then 25, 25 here. So you see, in terms of x-axis, the movement is like this, generally like this. Okay. This, and this. So if you even imaginary, if you do, you are going to look like your model is going to, you're supposed to build a model like this. Everything. Now, one more thing for all the people who are from computer science, and okay, one more disclaimer. Actually, AI, ML, and data science is not. It doesn't belong to any particular branch. It's not like that. It belongs to computer science or it belongs to AI, ML is its own. Data science and AI, ML are its own domain, where you need computer science also, mathematics also, graphical, visual, everything is required. That's why people who join AI, ML in colleges, only the top rankers should join it. If people for low rank and those people join, they'll find it very difficult because all this explanation, all this holding all this knowledge of algebra, analytics, and all, it's going to be too, not so exciting for them if they are not into math and everything. Right? So not to blame, and not everybody can become a well genius in this. So that's fine. Now see this, what I'm trying to draw here is, if I draw a curve anywhere in a graph, this curve is governed by an equation. Because what is this actually? What is this line? This line is a set of points. Correct? This line is a set of points, which means each point is a x comma y. Each point. So when you know the drift of this x comma y, we can remove this black color line and just write an equation for it. So that is exactly what is now happening. I'll just remove this. So what am I going to do here in linear regression? My intuition for linear regression is going to fit a straight line. This, you can tell me, this line is better. Is this a better model? Do you think this line is a better model? One or two? Feel that, okay, if you take two, then this is very far. This is also very far from this. This may be nearer. But if you take one, you have four. If you just remove the second one from here, it looks, this line is nearer to most, but that other line wasn't. See? So when I do this, when I choose the model 1 as the line 1 as my model, what I say is that I have line captures this line, which now I'll ask you a very technical question. Okay. Which line captures most of the variance? This is how you ask. Is this line capturing most of the variance? Variance means what? The change between each other of the data. Which line is capturing it better? Line 1 or line, yes, line 1, right? Because, so that's the whole idea. You create a line which captures maximum variance in the data. That's the linear regression. But that is all there is. That is all there is for all kinds of machine learning algorithms. You are trying to capture, you're trying to build an equation which captures the entire variation. This one. So if you want to now express this particular line, if you want to express this particular line with an equation, what I need salary is equal to sum m into age bias, which is your C. Now, where is the bias? The bias is here. This, when it is cutting here, no? This point is the bias. Now, if suppose this point, this line I have drawn here, no? Can I reshape this? Okay. Let me get a few more points. Suppose the data was like this. Now this is wrong. Now what happens? I will like to draw this as my. Let me just draw the green line. Okay. The third one. Now, don't you think this line is much more better because it is captured in essence? In fact, we don't know. Let me put a shape. Is it okay, or should I? Can I do something else? Can I shift this here, and can I shift it here? We are mostly trying to get all of them together. Now this whole thing gets this whole variation, right? From here to here. Entire variation is getting captured. You want better than. Yeah. What happened from the previous one? The intercept, the bias was here. See? Now with the new model, where is the bias? So basically, when you turn something like this, no, changes M. When you're fixing the pivot and changing the slope, what is changing? The slope is changing. So that M change. So where should it stop? If it stops here, why should it stop here? Why should that model stop here? Model, what it does is it will first start with one assumption. Okay, is it the break time now, guys? And how many of you want to go for like a 10-15 minutes break? Now I'm going to go very deep. Even if it takes 2 days extra, doesn't matter for me. I will go very deep so that you are at least happy that you have conquered this subject for the rest of your life. I hope you're all okay with that. Because if you understand everything fine, right? At least the first 3 days. Rest you will, if you just see the video, you will understand. Because fundamentals will be very clear. And thank you all, just having so much patience sitting. And so let's go for a break. 15 minutes. It is 10:30 now. 10:45 we'll be back. Okay. Then I'll continue this. And I want to make sure that you guys will understand everything properly. Don't worry about it. The next episode. See here, are trying to fit this line. But where does this line start from? Now you think the Python's perspective of this. Copy this. Paste it here. Now, if I tell you that this regression, this problem is optimization problem. Under optimization, you have two aspects. You minimize something and you maximize something. Okay. What is this line trying to minimize. This is the starting point. Okay, this is the starting point. We assume that this is the starting point of the model. Model assumes this is a hypothesis, first hypothesis. This hypothesis what do you feel about certain thing? That's your hypothesis. You don't know for sure, but you have a guess. Hypothesis is a guess. So when you ask Python program and you say, hey, build a linear regression model between X and Y, where Y is my dependent and Y depends on X, which is independent, then what it does is first it frames a hypothesis that let's say this is the model. But now let's evaluate something. We are going to evaluate the distance of each point from this proposed model, including this, okay, including this, the distance from its, and it will shift. So your Python code will shift like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. This is very important. This concept stays forever, no matter what your algorithm is, whichever algorithm you use. The concept that I am teaching you is a base core concept for all machine learning algorithms. So I hope you guys are all attentive. It started here, and at this point, make a note of all these distances, square it. So we call it sum of squared. Sum of the squared distances from should say sum of square distances of the data from the hypothesis. Okay, you understand this hypothesis word is very important because at one point of time we are going to do something called find S. This algorithm requires algorithm to output a description of all set of all hypotheses consistent with the training example. So this is the same hypothesis. Okay. In this case, your hypothesis is that by looking at the data, you felt that a straight line would fit. It's a hypothesis. We started the straight line here. Python. Slowly, it is supposed to do what? It's supposed to shift 1, 2, 3, 4, 5, 6. So as it moves, this value keeps changing. From here, you have an SSD, sum of squared errors. You shift again, there's a sum of new squared errors comes up. Let me put that in a different color. Where's that line? Okay, then let's keep this here only. And we shift. So when you shift here, there's a new perpendicular line computation that happens. I'll put that as which other color is so well. Lines. Perpendicular, Euclidean distance. And what is this distance? Is that this is also x comma y. This point on this also is one x comma y, correct? If you do this, let's suppose you take this line. You want me to zoom in? So this is one line. Okay, this is perpendicular. This is another line. It was perpendicular to the previous hypothesis. From here, it was a perpendicular line. Now it shifted. You see, from here to here, there was this shift. Correct? Is this, call it a step size. So we are going to uniformly shift step size. And a new computation gets done. This time it has crossed, so it is negative. This time this is negative distance, is positive distance, because we crossed one point here. Okay, now this value is a negative value. That's why we square it, because we want only the absolute distance of this hypothesis which is moving. And what are we eventually, when are we going to stop? Are we simply going to go up like this? When are we going to stop? Going to stop when you have minimized the square distance. So at some point of time, you have minimum square distance. All the points, because you're computing distances of all the points, right? Here, we check the SSD, then moved one step, then we check the SSD, then moved the next step, then we check the SSD, then we moved even further, then we check the SSD. So what is moving from here to here, here to here is the slope. When this changes, slope, which is equal to m, changes. If you want to really go even more deeper into what this slope actually means, so I'll show you. The slope here, suppose here, see, the slope here, you set off a slope here, and okay, this, the ratio of this and this is the slope here. What is this? Change in x, that is dx, change in y, that is dy. What is it telling you? Dy by dx is the slope. What is it saying? It is saying, see, this is a number. You get a number actually. Okay. Here the number will be how far, how big is dx? Very big. How small is dy? Very small, right? The big number, small number divided by big number is, you will get somewhere 0.2 or 1. What it says is, to get some change in y, you have to traverse so much of x. This is a proportion. How much proportion of the change in dx will be effectively contributing to the change in y. So that ratio you put here, that ratio gets into that equation. Okay. Now, this was moving and it came here to a very good fit. But somehow we felt it can be better if I shift this from this value to this value and then bend it like this. So what happened? The previous, now from here to here, there was a shift. This is your C constant. So you keep shifting. So what you actually do is, you start here, you check, then you shift a little, then you check, then you shift a little, and then you check again. Who's doing this? Python, that linear regression program will do this only. Every time it will change the C and keep changing the slope. What? To minimize the square distance error. This also can be seen as a maximization, because what we want is, we want to maximize the number of nearest points on the line. We want to maximize how many points are on the line. So this problem is an optimization problem where you are doing both. You are minimizing the square distance, sum of the square distance, or you're maximizing the number of points falling on the line. Now, one more interesting stuff. You see this shift 1, shift 2, shift 3. Who will decide what this shift is? What if you decided a very big shift from here, then here, then here? So don't you think we would have missed an optimal position there? From here, if you shift double, let's say your shift point, that is your change of slope is 30% for every shift. So you are going to end up with the next iteration, you'll come here only. You would have missed this position. You'll come directly here. Next iteration, you'll come directly here, because that's a big shift. But what if your best model was here? No, but you never accounted to come here at all. Are you following this? Are you all appreciating the meaning of this computationally? 2 thumbs up. Everyone who is not appreciating, put 0. who's not connecting at all. They don't know head or tails what's happening. Who feels like that now? Put zero. It's okay if you put zero, and again I'll just explain. Zero. Oh man, Vedaji, zero. Okay. Okay, fine. Okay, so you'll understand. Once I finish this, hold on. I'm telling the person who's put zero, I'm telling you, hold on, it will start making sense, okay? When I do, when I reduce this equation to the equation, it will start making sense. One shift, second shift, third shift. So it is very important for us to set this step size low. What is this setting of this step size called? Can anyone tell me? I'll give you a hint. You can tell me what. It is made up of two words, L and R. First letter is L, second word is starts with R. E, A. Anyone? Anyone wants to fill this? Learning rate. Fantastic, Shalini ji. Fantastic. Learning rate. Super. Okay. So you are, that is why you will see a lot of learning rate issues in this one. So you set a learning rate. Now, what if I do something very intelligent? What if I build a program where, see, when I shift from here, we know what is the sum of how with one step size, right? We can just shift from here, and we know what was the sum of squared distances. Now we shift again. We know that sum of squared distances is easy, which is what we want. So next time we will not try to shift like that. So like what I'm trying to say is this. See, I want to shift like this. I'll show you the picture. I'll show you the way in which I want. I mean, you will appreciate that if something can do this, then it is amazing, right? So I want my shift to be first like this, then check the sum of squared errors, then go a little slow, then go a little slow, then go a little slow, slower, slower, slower. Who will do this for us? Which algorithm does this? G, D. Who wants to tell me? Perfect. Perfect. So that gradient descent algorithm is going to create a gradient for the descent. Okay. So this gradient descent algorithm is at the core of everything. Gradient descent. Okay. So if you want to visualize the gradient descent, let me see if I have this. Is one of the things that I had given with SVIT. So, okay. So starting point, slowly, you see, this gradient descent, slowly, this gradient descent algorithm, slowly it will converge. It will converge at the optimum weight, WI. And what is that optimum weight here for us? Optimum weight for us is M value. There it is W, fine. But here my weight is M. So it is going to slowly converge at M. So when you see this, the loss is your SSD, square sum of squared distances. Every time your loss is decreasing, and slowly the value of the weight is increasing. But after a while, if you keep on increasing the slope, again you will start moving away from it. That's what is happening here. If you keep moving like this, you would have reached the global minimum. But if you keep on moving again it will go further away. Right? So let me just copy this, put this. Loss derivatives. Starting point, slowly come down. negative gradient. See, that's what is happening. Negative gradient, gradient, reducing loss, learning rate, all these concepts. So finally, you are coming here. And if you keep moving ahead, you'll keep on again going away from that. So you want to find this, the minimum weight that will give me maximum number of points on the line. And whatever gradient descent I just taught you, it is fundamental concept for all. Ladies and gentlemen, please share the gradient descent note. Okay, this problem is a problem here. I'm not able to share this. I'll try though. If I can get it into a, this is here. You can check this. If you want, you can check this from here. I'll send you this link. Of course, I'm not creating everything, right? I'm also taking it. So I'm going to send this here for everyone. See, I've sent a link. If you go and click on this, this is a Google's playground. So nicely they have shown. Wow, this is the they have updated this page. Earlier it wasn't like this. Updated page. Sent you the link, huh? So machine learning, Google has created this, and if you want gradient descent example, go and watch this. Calculate the loss with current weights and biases. Correct? Calculate the loss. It is calculating, determining what is that. Everything is pictorially arranged. You can check this. See, every time we are shifting, we're changing, iterations, what is happening for every iteration. You can visualize this. So you can, yeah, this is enough. If you can do it. And if it is only 2-dimensional, you have a graph like this. If you're 3-dimensional, you have the solution is not a line, the solution is a inside a 3-dimension. And it's 4th-dimension, we cannot visualize, but in 4th-dimension, the solution is a 3rd-dimension, a cube. Okay. And so on and so forth. It moves on like that. Of course, as you keep on moving ahead in the dimension, you are going to need complex computations, and that's why linear algebra comes up. This simple algebra cannot handle it. Okay, so that's the connection. Let me just try this for somebody who said not able to understand y is equal to mx plus c. Yeah. So what is the equation of a straight line? Y is equal to mx plus c. So I am just trying to fit the straight line. That straight line is supposed to do one thing for me. What? It is supposed to minimize the sum of squared distances or maximize the number of points on the hypothesis line. So when you have minimized SSD and maximized the number of points, that hypothesis is closer to the truth. Now that line is the model. So in this case, this orange line where we fit in, this orange line is our model. And at this point of time, we'll calculate what is the value here. So 0, 1, 2, something like 2. 2 is good. Okay, 2 is your C. And this slope is, I think the slope, what I'm seeing is I can get the slope field here only. I don't have to even compute. You see this? This is the slope, right? I can get the ratio here. How much of this is here? This one, if you make a proper right angle triangle, use this 2, 3, 4. So 4 parts here, 1 part here. That is 1 by 4. So your slope is 0.25. So now it is very simple. Now what happens? Your salary equal to 0.25 into age plus 2. Yes. Check what happens. Let's say we want to predict the salary of a person who is 20 years. What you will do? You'll take 20 here. you multiply it by 0.25 and add 2 to it. So 20 into 0.25 is of 20, which is 4 plus 2, 6. Somebody who is 20 years will have 6 LPA. What it is? The new value is 20, 6. So go and 20, this point we got. Why? How? By just giving this. Who gave this point? Because to put a point, I need both x and y. I just gave x. Y was given by my model. The model is linear regression. There are certain metrics. What metrics we have? We have a lot of metrics. We have value. First is the slope. Okay. Then you have the y-intercept. Your C is M. Next, one more computation we want. What is that computation? We want how many points are on this. So we say squared error. Nothing but a SST. Okay. Then we have root mean squared error. Root of your mean squared error. Then you have something called standard error. That you will see here. This is my version of this one. See, slope, intercept, R value, P value, standard error. Slope you understood? Anyway, let me show you this problem here. This is this is not your Python laboratory problem. This is what we teach. Like the first time when we teach linear regression, we teach like this. We don't take any data. We take random data. Okay, we manufacture that data here only. And I've got this data here, which is plotted. You see, this entire data is very nicely structured. And on that, the line is there. Nice fit. Okay. But what I'm trying to tell you is, you get stats from stats.linregress. You put a feature X and Y. Like X is page speed and Y is my target. So I'm trying to build a model where I can, if I give you the page speed of a website, how much purchase can be done by the person, right? Or the customer. That's what it is. When I do a stats.linregress on it, I will get these values out. The work of this linregress module is to calculate the relationship between page speed and purchase amount. What is that calculation? This. So this. Here salary and age was there, but in our case, page speed and purchase amount is there. Okay. So it will do all of this and it will come up with the values. Slope, intercept, R value, P value, standard error. Let me copy this. Let me copy this and let me paste it here. Now, all these metrics are important. Slope here. Intercept is here. R value is the sum of percentage points, number of points which are actually falling or very close to the hypothesis. Your hypothesis is the line. Okay, so you'll get some value, you get slope value, you get intercept value. Using this, your model can be built because that's what you needed. You needed the slope and you needed the intercept. Extra values are to evaluate your model. Value, it will say if in this case 100% of my data was falling on the point. You see this R value. For this, the R value is for this, the R value was R value. Okay, this is R squared by 0.99. Means why 0.99? Because 99% of the points are falling on the model. So model is able to capture the entire variance. Are you understanding the language now? Model is capturing the entire variance. Perfect fit. 0.99 fit. Those computations that we did, it says that if R value is very high, your model is nicely fitting. What is the P value? P value is not there, but anyway, since you're seeing this, you would like to. When you said your hypothesis was a straight line, value says how wrong you are, probability of your hypothesis being wrong. This is a statistical concept. Are you guys understanding? How many of you understood what I just said? The probability that you are hypothesizing wrongly. Because when you see the data, all you have is a guess. Whatever you guessed, what is the probability that your guess is wrong? That is the p-value. So you see in this, you will see p-value is 0. Means probability of you being wrong is nil. How many? I don't know. And usually R squared and p-value will be opposite. If R squared is very high, which means your choice was right, which means the probability of you going wrong is 0 or coming towards 0. So that's what this is. Now, one more concept that you have to understand is standard error. What standard error tells you? Do you guys want to understand what standard error is, or can we just move on to the code there and finish it? Otherwise, I will just ask you this one. No? Okay, we'll just move on then. Just type in 1 if you want me to explain. Okay, standard error. It's like the data science thing. Data science statistical problem. It is standard error. What standard error says is that we appreciate the fact that these data points are here. We also, before only when we started, we knew that our points, all these salary data points are coming from where? Coming from this problem, right? Somebody from Electronic City to Majestic, from BTM to this one. Data that you collected was just a sample. We know that the model that has come out of this, where is that model? Here. Salary is equal to 0.25 age plus 2. Model will not be utilized in predicting the things that you already know. Will it give any value? Will it be of any value in this world if you are using this model to predict something which you already know? There's no value in it. Nobody is going to pay you for that. They want to predict the salaries of people whose data is not there in your training sample. Not even in training, it is not even there in the testing. Because whatever you got was only a sample of the entire population. Population data can never be collected completely. So we want that model to be effective in the real world. Okay, whenever it goes, whenever you test this model in the real world, you want this model to perform well. So now I'll ask you something. You have to answer. You have to, when I say yes, you're 1 0 1 0, because then only it'll make sense. Understand the variance here? 1 1, yes. Do you understand? Are you able to visualize the variance here? The variance in the data? Right. You are able to see it. You are able to see the variance in the data. In this sample itself, there is so much variance. Imagine how much variance will be there in the population. You appreciate the question? in P if you're appreciating it. If you're not able to appreciate it, then you can type in N, because the appreciation of this problem is the route to understanding standard error. What I'm saying is, in the simple sample itself, just what, 1, 2, 3, 4, 5, 6, in just 8 data points, if there is so much variance, imagine the amount of variance will be in the population. That too, if you get into a bus which is going from Majestic to Vijayanagar. Okay, of course, these are all places in Bangalore. Okay, so if you want to go, or something which is going from Majestic to Tumkur, okay, you will have different kinds of people there, right? There will be people who are working in IT, there will be people who are farmers, there will be people. So your age and somebody who's at 35 could still be earning 5 lakhs. But somebody from 35 could be earning 35 lakhs also. So these data points are like spread everywhere. This is very nicely done. So the standard error value says whatever prediction. So it's a statistical modeling. Okay, statistical estimate it is. What it estimates is that if the sample itself has so much variance, it will have an estimate of the variance that can be found in the population. Then it will say, was for this much variance, your model is good. But if you try to take this model and work it on the population, you must expect some error to be there. So in your prediction, there will be this much error when you fit an R squared of 98% or 99%. If I change this formulation here, what I'll do, just okay, I can change this. Maybe just let's see. Yeah. So now the data is like this, scattered. Now see the values. Now what p value is telling you? 84. You are 84, 0.84. High probability that you're wrong. Yes, because when you see the scattered data, why did you think that the straight line will fit? Will a straight line fit? No, that's what this p value is telling. Because the intercept is here at 50, it is giving you an intercept. Fine, the slope is very, very less. 0.08, hardly anything. Standard error is every time you make a prediction, you're 50% wrong. 0.44, right? So whatever you think you predict, add 0.5 more to it. 50% more. If your prediction, if the predicted number is 75, you can expect the value to be between, what is 0.5 of 75? 30 is 70, 37.5. So if your model predicts 75, the reality could be anywhere between 75 minus 37.5 is 37.5. 35 plus 37.5 is 12.5, 112.5. So between this and this, it could be. That's what it is saying. Because it saw that sample itself is scattered. Imagine the population. Now you're understanding, everybody? Making sense? What standard error is? So these are all the key concepts in industry. All this are, even in industry level, this one is very deep. So because all practical, right? So every day these decisions will be taken. So all this is combination of stats, machine learning, coding, pandas library, and all that. So it's fun, but no data scientist can ever say that I am a great data scientist and will you give me any model, I will fit 99%. How? If the data itself is like that, how can you fit? Correct. So I hope you're understanding that there is no beautiful skill. There is no amazing data scientists or ML engineers who can fit a data better than somebody else. Your model is only as good as your data. If the data is very scattered, there is nothing you can do. Some things we can do as a good data scientist can practice the process properly. Document it saying, hey, see, we conducted everything, we calculated the standard error. Something is there in the data. We'll have to bin that data or do cross-fold validation and all that topics come up, right? So then probably we can, in parts, maybe we can do better. You can divide this whole thing in different classes, and this is when you go for unsupervised learning. When your prediction, your intercept, and everything, the R squared value is next to nothing. Where's your R squared value given? R squared 0.006. If your model is so bad, there is now the problem is take it as a unsupervised learning and then see where there are clusters. And there are clusters, there are different classes. Then we say, Acha, at least let me try and see if I can predict the data for a particular cluster. Then you divide the problem and tell the client that, okay, see, in parts, I'm able to build a better model. So you tell me why these people are clubbing together. Then we come out with the analysis saying, for this analysis, we are saying, Acha, in this data sample, if your model is not performing well, it means there are different classes of people. So we come and say, okay, I can build a linear regression model properly for techies. Then I'll say for properly for farmers. Then I'll say properly for lawyers. So then the model will be different for different classes, right? That's the whole idea. Yet we are not able to, at least, what the goal of this whole thing is, if you understand this core concept, when you are teaching, when you are learning, and when we go back to our problem statement here of Boston housing, at least now you're able to appreciate what we are trying to do here. Here it's also same. You see, MSE, mean squared error, root mean squared error, R2 is good, R2 score. Same thing, you already saw that. Of course, the standard error is not a part of this. We can add standard error also. Because I'll send you, if you want, I'll send you my codes also. You can use this code to teach your students and then finally teach this so that step-by-step things are proper. Is that fine? So we have understood linear regression now. Anyone wants a quick recap? 5 minutes. Eight minutes ago, there was a raised hand. Radhika had a raised hand. One. Chetana V. Patilji, please, you've raised a hand about 10 minutes ago. Anything? Any question? Anything here? Things that you have to focus on. Learning rate. And this learning rate is very important. Huh? This learning rate is a deciding factor. And this learning rate is calculated by a gradient descent. It will learn, it will understand. But still, you need to give a starting learning rate. After that, the gradient descent algorithm will understand. See, the entire machine learning is about how your gradient descent algorithm performs. And if you don't believe me, even deep learning has a gradient descent. Every machine learning model in this world, which will be built later also, is always you start with a guess and you get closer to the truth. The journey from the guess to the truth is undertaken by gradient descent because everything is an optimization problem, whichever algorithm you take. Naive Bayes, decision trees, your the find S algorithm, K nearest neighbors, everything is all calculation only, no? You have to appreciate the fact that everything, eventually the text also gets converted to numbers, image also gets converted to numbers because it's a number game, because computers can only deal with numbers. And we have made the computer with all this analytical geometry and all these beautiful packages, we have made the computer appreciate algebra also. And with all this new computations that is there, we can make the computer appreciate calculus also. So this combination of data, algebra, and calculus is machine learning. So you can appreciate now that the kind of, if you want really for the students, in fact, if all of you are here, there are so many people, so many lecturers across. We have a program for foundations of machine learning, where we only talk about analytical geometry, calculus, differential equations, the physics of it, the math of it, right? So that people who really need that foundation can get it. And we can, if anybody wants from here for your students in your college, then you can definitely come and conduct that. in either ways, online or offline, whichever way. But this is important. Otherwise, if you don't get this context, then everything will always look alien to you, right? Let's go to our, at least let's get one further going, right? Not much here. See, we understood the data, simple. And then what is that? MED-V. MED-V is the median value of owner occupied homes in thousands. Median value of owner occupied homes in thousands. So 24,000 owner occupied homes are there in one of the township. That township's crime rate is this much. That township's NOx or RM, where the nitric oxide percentage, the Charles River index, average age of people, and distance to the next, what is that, the computation center, and all that tax amount for that property, whether it is near river or not there, or disposition, or what is this here? Weighted distance to Boston Employment Centers. Okay, that is a distance. Okay, and then RAD is what? RAD is index of accessibility to radio. Okay, it's all here. So you understand that this is there. Now what happens? You can do the usual stuff. You know, the data.shape. Fine, it will give you 506 in the columns are there and 506 entries are there. Fine. Data.info, it will give you, okay, so many non-nulls are there. So it means there are certain null values inside. Correct. Dataset contains 506 entries and 14 columns with 6 columns, blah, blah, blah. And most columns are continuous floating point 64, while RAD and tags are discrete. It gave everything is that is what it is saying. See, floating point, and these are RAD and tags. RAD and tags are everything. Everywhere you will see only integers. Okay, this is what index of accessibility to railway highway. So 1, 2, 3, 3. Okay, fine. Other numbers are decimal numbers. So you just saw that continuous at this. MEDEV is medium home value. Is a target variable like influenced by features like RM, average rooms, LSTAT, lower status population. Medium home value, MED-V is $24,000. In thousand it is. The home value where crime rate is so much and Z and Indus, chaos and all this, the $24,000. That's the median value of the housing in this area. So like that. Now we want to do, obviously, what do we want to predict? We want to predict. How do we decide about the initial learning rate value? Sandeep, it is just a random seed. We don't decide on it. We just start somewhere because that is gradient descent, right? You start moving slowly and then you decide basically. It's like you're riding a vehicle. You start with some speed, but eventually the traffic will decide for you, right? Because you're taking feedback from the traffic, visual feedback. So you'll slow down, correct? So like that, you start with some value, then we adjust those values. It doesn't matter where you start from. Usually it starts with, you can start, there is an adjustment. If you want to start with high value, you can start. If you start with low values, you can start. It depends. It depends on the variance in the data. So that is one of the reasons. So that's a good thing. Sandeep Kiriji, I hope you're understanding this. If the variance is too much in the data, you can start with a higher learning rate. But if the variance is very less, start with a lower learning rate, at least your model will converge faster. So I hope you're understanding. Variance means so much differentiation is there, right? If the variance is too less, then it is fine. You start with a slope. But if the variance is scattered like what you saw here, start with this, then how does it matter what kind of learning rate you start off with? You start off with here, then you come here, then you come here, when you come here, then you come here. Whether you're going slow, fast, doesn't matter, right? Because you will never be able to capture all this variance. So I hope you're now understanding the type of language the data scientist uses. Is your model able to capture all the variance? At least 90% of the variance has it captured. If it is capturing 90%, then the model accuracy is 90%. That is, if it is 90% on the training data, then what about on the testing data? You will see a reduction. you'll see a reduction of 80% of the model fit. Then what you'll do is, sometimes what happens? Sometimes I'll show you. You guys want to go a little more deeper? How many? I can go as much as deep as you want. There is a whole universe in linear regression. How many you want? How many you want to see the next level? How to decide where to stop? How much accuracy you want to learn? Okay. Let's go. Hope everyone is okay with deeper. Can I see few more yes for going into the depth? Try to see at least 15-20 people say. Otherwise, this is again, yeah, this is deep, but then you will be as good as anybody in the industry. I want that. I want you people to be as good as anybody out there. Okay, fantastic, right? So look at this. Let this be the given data here in the first slide. This is the given data. Okay. Let this be the given data again. Now what happens is randomly I have chosen a few points. Blue dots are training data. Pink dots are testing data. Okay. In this, because that's what we do. In the given sample, we take out those points, right? Then this is training, this is a testing now. Okay. This training data is used to train the model. Testing data is to evaluate the model. So whatever model you develop here, it should come here properly. Okay, making sense? So now let's separate them and build a model. Apply linear regression to this. So when you apply linear regression to this, you get this line, right? This is your model which was built on what? Built on training data. See, same data, training data. Now, training model, let's apply polynomial regression on it. Okay, let's apply polynomial regression on it. Here, this is linear regression. This is polynomial regression on the training data, same data. Okay, there is no change. You see this blue dot, see the blue dot, exact copy it is. When you do a polynomial regression, the difference, of course, we are coming to polynomial next, so I'll cover it here only. The difference between linear and polynomial is you don't give much freedom to the linear regressor to cover and go across these points. But a polynomial equation, which looks like this, is not linear regression is only one, y is equal to mx plus c. But for polynomial equation, you have many x values. Why? Because between this point only there is one line. Again, there is a change of line. You see this? There is polynomial. From here to here, there is one line. Then again, from here to here, there is one more line. Then from here to here, there is one more. There is one more here. Then there is one more. Then there is one more. Then. So what is this? This is the addition of all the simpler linear regression. In how much value, the twist here, right? The change of the direction. This change you have to have one variable, right? To hold that change. So this small, ax, bx, cx, all these things, and it will give you this. Okay. So just so that you can visualize it even better, I'll open up our polynomial regression. So this is one of the polynomial regression. My polynomial regression. So you see, I've done a np.poly1d, np.polyfit between x and y and 3. I get an equation like this. This is not y is equal to mx plus c, correct? Seeing this as y is equal to mx plus c, this one, no. This is a very complex polynomial equation. What is the use of it? The use of it is you can completely fit the curve. You are giving the degrees of freedom. And that is also a metric. That is also fed in. So when you say 3, see a polyfit, A linear regression had only x comma y, but a polynomial polyfit, a polynomial regression, you have to give one more value where you're saying, I will allow you 3 changes. So with the 3 changes, I got this fit. In this case, any changes are here? Can somebody comment in this polynomial regression? Many, right? You can have 1, 2, 3, 4, 5, 6, 7. So 7th degree polynomial is required. Here, a 3rd degree polynomial was enough. To what? To capture the, type in the answer. A 3rd degree polynomial was enough to capture most of the, fill up the blanks. Type in. If one types in, I'm happy. What did you capture? Most of the, anyone? Are people there? No? Am I audible? All those people who said go deeper, I'm expecting an answer, please. What is this polynomial capturing? Most of the, nobody. Why you didn't know that? It is capturing most of the variance. Okay, that is what you are doing with polynomial regression. Okay, now even more deeper. This built on the training sample, you built the model. Now try and put it on the testing data. Built a polynomial regressor. You gave every freedom for it to cover the entire variance. See, where is the variance high? Where is the capture better here? This is better or this is better? This in training data. This is in testing. When you're training, which one was better? Linear regression is able to capture or polynomial regression is able to capture? Which one is better? Type in Q&A, you can type in. You can type P or L. In testing, if you write, do you think P polynomial regressor is a better model because it is covering all the variance? Is it not? Oh, this refresher is not happening. Yeah? Okay, you're all answering, but I'm not able to see it. Dimensionality reduction. Oh, okay. No, dimension reduction I'll teach you later. There's not too many dimensions are not here to reduce anything. P, yes, P is better, right? P is better. Now, when do we say that a model is overfitting or underfitting? Right. Manjula VG, right. This is the overfit. This is an overfit model. That's what I want to show you. Okay. Linear regression, you didn't choose linear regression on testing data, but now I'll show you. When you take this model and bring it to the testing data, on testing data, 70% accuracy is there. But you see this, the same model came here. Is the same model on testing data. But when you check this, none of them are actually on the line. At least here, although on training data, your linear regression wasn't really good. Just it was 80%. And you decided, no, I will build a polynomial model for it, where in the testing scenario, I'm getting 98%. The testing accuracy it is called. I'm sorry, training accuracy. On the training data, your model is 98% powerful on training data. But on testing data, the same powerful model completely gone. But your linear regression, although it was less on training, it is behaving better on testing. What we did here is by using linear regression, we ignored a little bit of variance. We don't want to capture the entire variance. Because if you try to capture the entire variance in the training data, you will have a high standard error in the testing data. Because if the training sample itself has so much variation, population will have a very high variation, correct? This is called bias variance trade-off. Make sure testing won't work. Yes, right. So this is called bias variance trade-off. You trade off the bias and the variance. You build a less biased model. A less biased model is this, because it is not trying to capture entire variance. If a model is not capturing the entire variance, it is called a low biased model. Bias is less. If your model is trying to capture the entire variance of the training data, then it is called a high biased model. That is, so when you trade off, when you ignore a little bit of variance loss for the overall greater good in the testing time, there is always a balance between how much bias and variance you as a data scientist is willing to allow. Fits perfectly well on training data, may not always perform best on testing. Why? Because testing is generated from different population will always have inherent variance and biases. We cannot capture, we don't know. That's why we trade off. Okay, hopefully this whole regression and hopefully a little bit of polynomial regression is also covered for you. What is the internal working of it? Basically, for polynomial regression, you are giving more degrees of freedom for it to move around. This one you are not giving, you're saying just fit a straight line. I'm okay if you don't cover the entire bias because my actual performance is on the real world. Okay, so let me get to the so this is my version of polynomial equation, simple R squared. Again, for polynomial also you have R squared value, you have to work on that, correct? So the model is here. Is built, which is nothing but y is equal to mx plus c, and how difficult it is to build a y is equal to mx plus c function. Very simple, right? Function output is a y, and you take m into the independent variable plus bias. That's what we did here also. Is nothing but return slope into x value plus intercept. There is no lint regress. This is a function, and lint regress gave me all these values. We did a lint regression. From lint regression, I just got this. I got slope, intercept, r value, p value, standard error. Fine. So I get this one, but also I think I can another this one we can directly, when you build a lint regress here in the example that we have built for Boston Housing. In Boston Housing, when you see we have all this data, and we choose median value of the home to be our target. How do you choose that? Okay, I'm shifting now. I'm shifting from the deeper aspects to the experiment 1. Experiment 1 and 2 can be finished in a flash because now you know everything. Correct? You know everything. So now that you know everything, fatafat, let's get to the code. Everything is self-explanatory, finding the unique values, finding the unique of CAS, all this we have done because when we develop the code, we want to check a lot of stuff. All this is there. You can use it or you can delete it based on how you want to conduct your lab. Okay. Now we have all this. Okay. We also saw that there are a lot of non-numbers. So we just take the mean of all the cream and fill it up with. How many people understand what I just did here? How many people? Give me a 0 if you don't understand. I'll answer. When we can go for polynomial regression, I'll answer. Now, how many How many of you are understanding what is happening in this piece of code? Zero. Give me a zero if you don't understand what is happening here. The NA. Okay. Let me 5, 6, 7, NA, 7, NA, 2, 4. This line, this is NA, not a number. Some symbol as value has come here. And this is one distribution. What I'm trying to say, if this distribution is CRIM, I'm trying to use, this is a part of pandas. DF comes from pandas. Pandas has a API called fill not a number values by taking the mean value of whatever is there. So Crim's other numbers are 5, 6, 7, 7, 2, 4. 1, 2, 3, 4, 5, 6. 6 numbers and divided by the entire 1, 2, 3, 4, 5, 6, 7, 8. And this is 5 places, 6, 11, 11, 18, 18, and 7, 23. 18 and 7 is not 23. It's 25, 25, 2, 27, 27, 4, 31. 31 divided by 8. Roughly about 4. So, in place of NA, you'll fill 4 and complete this one. So, this is data pre-processing. Okay. So, that's what it is. So, we do it for all. But we check. First of all, we checked it. Where is that? Is null. Sum. Indus had it. Trim had the sum of all the not a numbers. So when you see that there are null values, 20 of them here. So of course I have to do all this. So once you do this, now you check there are no null values because you filled it. But we cannot simply fill with anything, no. And another interesting thing is, see, cas fill NA cas dot mode. Right now, anyone tell me just by typing why mean was used here, why median was used here, and why mode was used here? Why not mean everywhere? Please, I would like to. No problem. See, okay, it's okay. Mode. See, when you have a data, we want see measure of central tendency was what? Mean, median, and mode. You see this all numbers, integers. You can calculate the mean of it. But see this rad. This is another index. Some distance from the rad was something else, right? What was rad? That was index of accessibility to radial highways. Okay. So index of accessibility to radial highways value was rad. Now here, take the mean value of this. Does it make sense when you take a mean value? All those are numbers, but are they continuously moving or are they classes? These are classes. So if there is a class, then you don't take mean because it doesn't make sense. Class, right? If you take, for example, okay, I'll just get back to. Okay, which one is better, black screen or white? Maybe black will be better because it will be good on your eyes. So we have, let's say, a class 2, 3, class 2, class 2, class 3, class 1, class 1. So if something is missing in between, let's say this is missing, can't take mean of this. Mean of this won't make sense. 2 plus 3, 5, 5, 2, 7, 10, 11, 12, 13, 14. 14 divided by 1, 2, 3, 4, 5, 6, 7, 8. Some decimal number, no? Eight, some 1.8. Wait, you can't use 1.8 here because there is no class called 1.8. That's why the creators of statistics said all moving numbers calculate the mean and mode and mean and median. But if there are class entries, you calculate the mode of it. That's why you're seeing mean and mode of it over there. Okay. So that's the whole idea behind this. I know. Is it not getting refreshed? But mean is good. This mean is not good with outliers. For categorical data, we use mode. Yes. Tajil Shah, you're right. Discrete values mode. Yes. Shubhi Agarwal also. There. Well, you guys know your stuff. Discrete or categorical values. So super. Super. For those who didn't understand, that was the idea of mean and mode. And Baki, what is there in this code? Nothing. We are not doing much work here. Our work is only to understand the science behind it. Baki, Python is going to do. Then if you want some, graphs to be plotted for each values, it's up to you. Plotted it just so that, your lab manual, your lab exercise looks complete. So sometimes, let's say you're giving a problem statement to build a linear regression, the student is not able to do. They would have at least studied the first two examples. You can ask them, okay, you've got a linear regression problem, at least do EDA on it. Or something else, at least something they will do. Now, correlation matrix, same way what we did last time. We understand which one has high correlation, low correlation. And this, because this is a heat map, your eyes will go towards the hot area. This is a hot area already. There is nitrous oxide and then there is Indus. Go and check. Nitrous oxide value is increasing where it is going with Indus. So you saw that. Now go and interpret it, why it is like that. So go and check what an Indus is. There is that Indus. Indus is proportion of non-retail business peak. See, so nice. Nitrous oxide comes when there are industries. And industries will come where there are non-retail business acres per town. Or non-retail business means farming. So nitrous oxide for urea and all that will be used more. So that's why wherever this Indus value proportion is high, your nitrous oxide concentration is also high. That's what the this one is. So anyway, we are here to do the linear regression on it. Fine. Now we prepare the model for linear regression. And I told you, when you want linear regression, what do you want? Any model, what you want. When you build a model, what is it that we want? X comma Y we want, right? Supervised model. Linear regression is a supervised model. X comma Y we want for this. Use the same logic. Come here. You want to prepare that X and Y. Now X is the data from where you drop all the MED-V. You have dropped the MED-V value from it. Which means, let me get this. The MED-V value, you drop it. Rest of them is my X. So that's why I said in that you have XY, but X will be its own. X will be its own. Y will be its own clear thing. Okay. Right. Moving on. Suddenly now you use a standard scaler. I've been using a standard scaler. Come back. Why is the standard scaler required? If we all are acting without class level attribute, correct? Absolutely. Okay. Why are we using a standard scaler? Standard scaler. Let's just look at, if you try to plot a graph between age and age of the people around that place and the nitrous oxide value. Okay, let's say tax value and nitrous oxide. Tax value is some big number here. Some black population. Okay, people, Afro-American population, right? B and E. Because the combination is useless, but just look at it. B and E. If you go and plot this graph, B and E. So standardization it is called. So I plot the B value here and the NOx value here. This B values will range from 0 to 500. And the NOx value will range. So if you divide it like this, 500 values here, your 500 values will be like this. And your 1 is here. So all the NOx values are here only. But your B value is spread across 500. So you have to scale it. To scale this entire 500 from 0 minimum to 500 maximum will be there, right? For each value, if suppose here it is 100, suppose here 250, 300. So this entire value should be scaled to fit between 0 and 1 proportionally. So that is what you take max minus min divided by min for everything. The value minus the max divided by the min. Okay, the x is sometimes x becomes 100, sometimes x becomes 330. Okay, so every time for every value we can manufacture a scaled value that will be between 0 and 1. So if the max is 500, and what is the value of 100 in terms of 500? In percentage. 0 and 1 is in percentage. It is a weighted scaling. So you're in between 0 and 1 range, your 100 will be like somewhere around 0.2. 500 will be 0.99. So you're completely putting new 0 points. And now what happens? The scale now suddenly zooms in, where both NOx and B are between 0 and 1. Now you can visualize some graph. Otherwise, can you visualize a graph which is here? It happens many times. So always be careful. You have to scale it so that some rationale for the machine to capture the variances. Otherwise, we can't even, it doesn't even work. Okay, I hope you're appreciating the fact of scale. So improved model performance, linear models assume the features are normally distributed around the mean. Linear models assume that the features are normally distributed around the mean. Scaling the data can make the algorithm converge faster and produce more accurate predictions. Normally distributed around the mean is normally distributed around the mean. Means what? You know the normal distribution. It's like this. The mean and the first sigma, 66% data is there. The first sigma to second sigma, you have 13% data. When you look at this and you want to look at the data which is looking like this, your data will be like this. It is giving this. Whatever this area is there, no, this is that area. So distribution of this sample will look like this. For example, we assume linear models assume that features are normally distributed around me. Scaling the data can get the algorithm converge faster, and it prevents a bias due to feature magnitude. With large numerical ranges like tax and cream may dominate the model if not scaled properly. We don't want that extra domination where the bias is towards this. In regularized models, when standard linear regression may not heavily be affected, scaling ensures more consistent results. That is what. Anyway, you can have this copy with you. You'll understand. We have the next session from 12:30 to 1:30. Correct? We have time. I would like to close in both polynomial and feature and linear regression. We are in linear regression experiment. Part 1 of the experiment 7. We're almost closing it now. Everything you understood, why you want to scale. So you see, you take that x value and scale dot fit transform. X scaled has come up. Now what you do, you use trained test split. You method. Where did you get this trained test split? got it from the one which you imported. That's sklearn model election import train test split. So you got that from there and you came down to do a train test split. Once you put this, you have x scaled, comma y, test size 0.2, random state 42. Right? X train, X test, Y train, Y test, it decides on its own. And who decided whether it is 80% 20%? This one. When I say test size is 0.2, the test size is 0.2 of the entire data that is given of X scale. So we gave the X scale value, we gave the Y value, we gave how much is the test size, and we said random state is 42. Random state is 42 means what? Randomly pick up from the data, randomly you have to pick up the testing and training. You should not be sequential. So it does that. It does that, and then it gives you back X train, X test, Y train, and Y test. So then you have model. The model that you want is your linear regression, right? Linear regression is a third which is already there. From where? From scikit-learn. Okay, from scikit-learn you have already. Is it there here? Like how you're importing sklearn processing import linear regression, right here, right? Like that you have done here in the linear regression. So model.fit X train, comma Y train. Hold on, just a second. I'm sorry for the noise. We are actually in the middle of this circle over here, our office, and there's a lot of commotion, action, activities happening here. I'll try to sit in a different place tomorrow, so where there's less noise. So I hope you're getting the idea now. It's as simple. Bring the model in, then what are you going to fit? The model will fit X train and Y train because X train and Y train is already separated for us. So after that, you do ypred is equal to model.predict. You took linear regression and you transferred all of its attribute to a new object whose name is model. You can put your name also, doesn't matter. If you put your name here, then you have to put your name here and say dot predict. It will understand. Okay. But of course, for brevity and for clarity, we are going to use proper names. And then model.predict. Predict on what? Are you going to predict on, are you going to send X train here? No, we are going to send X test. Once the prediction is done, we got these values. We have mean squared error, Y test and Y predicted. Whatever Y test was there and whatever Y predicted was there, you have to clearly understand. Let me just not print this so that I've not printed this now, the predicted values. I'm just making you see the entire screen in one shot here. This is it. Okay. You split it. Train test split, you scaled, you put the Y test here, and you got X train, X test, Y train, Y test. You used the X train and X Y train. You use the X training, X values of the training, Y values of the training to build the model. Now in your testing, you have the X value and you have the answer of the Y value also. That is what your testing data stands for. You know the answers already. But now what you're going to do, you are going to build up prediction for Y using your model. You're actually saying, hey, for this X test, I already know what is the Y value. I know it, but I want to see my model also predict something. So I will send this X test and get Y pred. Now I will take this Y pred here, compare the Y test with my predicted Y. Already know what is the prediction for this X test. But when we put into our model, the Y, our model also said something. Now, how much nearer is my prediction to the observed? That is the value. That is the work of your mean squared error one. Mean squared error, right? Y test, Y pred. Then it will compare it and it will give you scores. Then you find the scores here and you got R squared error, R squared to be of much. Can you improve this? If you want, like, it's not in the syllabus, but if you want to improve this, you have to remove outliers. Outliers in all, you can check. I told you, the other day, when you check, when you do from every distribution, you take a distribution. You want to know how to improve this? To take all this data for each, let's say this is df A. For each of df of A, you find the standard deviation. And remove whatever data is there, remove the point which is at least 1.2 standard deviations away from its mean. In this normally distributed value, if you remove 1.25, all these outliers are gone. Only this will remain. When you retain only this and repeat this process, you will see significant improvement in your R squared value. That is significant improvement in your model. Okay. So with that, let's go for, okay, fine. Everything is clear. Hopefully I am repeating a lot of times. I'm pretty sure that today's model is object for linear regression. Yes, different units in data, right? Today, I think, yeah, we went, I was in a different mode. Actually, I thought I'll finish by this time. I think we are on time. Whether we like it or not, how much do we want to do? Right? How much did I plan? One is DPD 2. Oh, okay. I still have LWR. Then I want to do PCA also. Okay. At least next session, at least I would like to cover LWR. It's a long, this one, LWR, but it's easy. It's not, let's see. Okay, shall we? Yeah, break, please. Yes, sir. Yes. We'll come back at 12:30. 15, yeah, take 15 minutes. We'll come back at 12. Then I'll come back and I'll finish quickly. Polynomial is also same, nothing big. Same stuff. But only you are using polyfit transform. That's it. Okay. Anyways, so let's get back after a break and then we'll resume from there. Okay. As soon as I come back, remind me to turn. I'm pausing the recording now. As soon as I come back, somebody please remind me that I have to turn on the recording. Okay, I'm pausing the recording now. Guys, bye. Okay, so we are back from the break and we're gonna enter the last session of this day, where we'll close off at 1:30. We have 1 more hour. Quickly, let me see what all we can cover in 1 more hour. Linear regression recap. The data, understand the data, call the missing values, do the needful in terms of data cleaning. Then you divide and you watch some graphs to compare and see this one. Put a heat map to see the correlation matrix. Then the business starts here, where you separate all the X values by dropping the med V from the data frame, and whatever remains is an X. Med V separately is taken as Y. Now you have an X and Y. Now we have to transform that X, because we understand from the previous lessons, we have to transform it. The scaled data is taken here and separated into train test times. And after that, you call in the linear regression model, you fit the model. Once the model is fit, Y pred is already there. Okay, so model.predict X test is your Y pred. Okay, now you take that Y predicted value, will give you the model evaluation. So MSE is computed like this. RMSE is the square root of MSE. Then you have R2 score, which is R squared value, which is computed by Y test and y pred, same way. Okay. So you get all these values. When you see r squared value 0.65, it's okay. I mean, at least it is not overly fitting the data. But if you want to improve on this, then you'll have to remove outliers from the data frame. Okay, for each variables. You know how to use, you want to see that, right? You can see the outliers here. See the outliers for frequency and B, right? B is very high outliers. You may want to drop this. You don't want to build a model using the p value. So this is your indicator. If you have so many outliers, don't use this. Don't use this value at all. That's something which you can do as an exercise. If you want to do it, drop the box, drop the b value from the data and see how the accuracy increases. Same way, I think MedV is, of course, anyway, has its own outliers. So it has its own problems. That, when you see this, let's say this crime rate also has a lot of outliers. You want to drop this off. How do you drop this off? You decide 0.2 sigma away from the mean, 1.5 sigma away from the mean. There's actually a code directly. If you want, I can give you that function. That code, if you put the value automatically and set this one, it will drop it off. Okay. So the X is linear. Now we come to polynomial regression. Same thing. Same way we import everything. The data is different. Data is MPG, miles per gallon data. This is the car data. This is auto data. Okay. Develop a program. This is the part B of experiment 7. Program demonstrates linear working of linear regression and polynomial regression. This data set is polynomial regression. Polynomial regression use auto MPG data set according to the syllabus. So how do you get that auto MPG data set? You import C1 as SNS for visualization, plus SNS has your auto MPG. Okay. So now you get the data set names. You have all this SNS.get data set names is a inbuilt method for SNS. And in that, you have all this data inbuilt. Iris is also there. Penguins is also there. Planets, I think why it is typed in 2 times, I don't know. But yeah, maybe some different MPG, I don't know. So in that, you will find MPG here. One of the data set is MPG. Like that, you have so many data sets in SNS. That, and then see data is equal to SNS dot load data set called MPG, because we identified MPG here as a part of the data sets which is in SNS, and SNS is a object of the type package C1. So C1 I have invoked C1 as SNS. From SNS, I'm getting the dataset names. I identified that MPG is existing there. Then I come back here and load that MPG into my data frame. Now you have data.head. Data frame comes in front of you, and then there is a lot of cars, like Chevrolet, Malibu, originated from USA. Model year is 1970. Acceleration is so much, and the weight of it is so much. Horsepower, displacement, cylinders, and blah blah blah. Right. So that miles per gallon is what we would now. Now we'll go and check what have we done. All these things are just data.info. You get the info. No null, but it's cool. Uniques are so many. MPG uniques are 129 unique values. Cylinders, 5 types of cylinder cars are there. And models are how many, name of the different models. 305 different models are there in this car data. And unique, you want to see the data.horsepower.unique values. You want to actually print those values, unique values, you do this. Just data.nUnique will give you. Then data.horsepower.unique means the horsepower. If you want to check, you can do that. If you want to check the name, I'll copy this name. I'll paste it here. Then if I run this, data is not defined. So I'll have to run all. Then I think we'll get. Okay. Now I did a data.name.unique, and there are so many unique parts in our MPG data. Okay. First, hash it because I don't want to see all the unique values. Anyways, you clean the data, check if there is any null. There is no null. Any duplication? No duplication. Data handling, df.data.copy, df. You want to copy this entire to df. because we don't want to type df data every time. So df horsepower dot fill na. So I think horsepower had a little 6. Okay, null values were there in horsepower, so that's why just do the fill na. We learned that, right, using the median value of horsepower. So my median value of horsepower was mean also would do. It doesn't matter. So then you describe, you check all these stats value for your this one. Just doing it. There's nothing much. EDA, you want to put all this. How many numerical values are there? How many categorical values are there? You just check that, and then you go ahead and do all the usual computations that you do with the data. All this frequency and box plot for each of the variables. Then you import Seaborn as an SNS again. Then for columns in categorical, you do all these plottings. The counts are there. Different countries origination, but USA has highest cars. Okay. And then you do count of each of the categories. This is a count of countries. This is a count of type of the car, the model, right? You can do count of anything, but count is usually done for what? Count is done for origin and make. Okay, this categorical data. So there are two categories. One is we did it here, right? One is country wise and one is car wise. These are categorical values. So we wanted to count those. That's it. Then you do correlation on it between all this. So we check, okay, between horsepower and displacement. Where is horsepower? Horsepower is here and displacement is here. Means what? Means if the power is more, displacement is more. Making sense, right? And very light is miles per gallon with acceleration. Yeah, if the acceleration is high, you would see some effect. If the horsepower is high, then you will see acceleration. Horsepower and acceleration, how's the connection? Power and acceleration. Interesting. Acceleration, horsepower is a negative, which means higher the horsepower, lower is the acceleration. If there's a powerful vehicle, it's a powerful engine, the cylinders, immediately it won't pick off. But overall, the power eventually will be very high. But immediate pickoff is less. So more horsepower the vehicle has, the acceleration will be less. That's what we are inferring from the data. I'm not saying this. That is what the data is saying. Fine, that's cool. So what we do now, X. Well, now we build up miles per gallon with a particular X value. So take it X and Y, build a polynomial regression for it. It depends on X. That's how we are measuring this. We want to see a model. Miles per gallon depends on horsepower. How does it depend on horsepower? So that is the question. So when you do a train test split of this and then call in a polyfit transform. So you transform this X train, whatever this X train data is there, you transform that X train to a polyfit dot transform using a function, and you get a new, which is X polytrain, which is going to look exactly like X train. If you print both X polytrain and X train, they are same. It has been converted into a NumPy array instead of a list. This is a list, the NumPy array, because polynomial function can't deal with list. It can deal with NumPy arrays. List is very, very complex. List is very heavy. Only wants the numbers. That's all. Because why? Because it has to fit the curve like this, right? Imagine how many lines it has to compute. So if you're giving it a list, it is not going to accept it. I say, I can't handle the list. Okay, list is too much. You are giving me list dot this, list dot so many variables, so many methods are there in the list function, list module. So we cannot handle that much big data. So I want only the few attributes, the number attribute of the list values. So you convert it into a NumPy array. Correct? So we do that here. Where is that? We do that here. Okay, X polytrain, poly.fit transform X train. Got a new X value. To X value, you take it here. And Y value. Of course, you always know the model dot fit. This is where your model is getting fitted. To fit the model, you use X and Y. But in our case, we directly cannot use X because X train is a list. We converted that into NumPy array and we got it here. So we got linear regression model and then X poly test for the poly dot transform X test. Training is testing. We're going to do the same thing. Once that is done, we have Y predicted is equal to model dot predict X poly test. Remember the same thing we're doing. Remember, we're doing the same thing. Once you do that, you can visualize your data. What for visualization? Is everyone following or am I just talking to myself? Processing is required for structured data as we are using structured data. How, Chandana, you're asking me a question. Is data processing required for just how do you know if it is a structured data? Everything is structured only. So here, Chandana ji has asked me a question. Is data processing required for structural data? Yeah, this looks like a structured data to us. Which one? The MPG model. But we still don't know how many nans are there inside. We don't know. If we don't know how many nans are there, we have to check it. And if you find it, do the needful. Right. After that, I think most of the people will find it difficult to understand this scattering. I don't know how you people will ask your students to by heart this because I am very, very bad at by hearting. I have a logic system in my mind of what has to be the constant, what has to be the variable, and we work on that. In industry, it is different. Nobody expects you to by heart it. So you'll have to be very careful in what you're expecting from the students here because this visualization thing is usually common. They can't remember these these libraries plt.scatter. No matter how much you practice, will not be able. Myself, my personal opinion is I can't remember this. I need the documentation. Once I look at the documentation, I'll adjust the codes. Okay. So visualizing the result plt.scatter x comma y color blue labeled data. Okay. So the label is blue color is labeled as data. That is a legend. Scattering the x and y. What are the x and y's? X and y's are your actual data. We have not even split that into X train, Y train here. The real data that we got from MPG, where MPGs and the horsepowers is all the blue dots. Because now I want a model which can follow this curve like this. So then I said X range is equal to np.linspace X min to X max and give me 100 and reshape it into this matrix -1, 1. What I'm doing here is, how do I say? You will understand when we are plotting. You are plotting the prediction. This values. Predicted value is this. So we take the X range the polynomial version of the X range values. What is X range? X range is the list that contains 100 points, just random 100 points between the minimum value of X and the maximum value of X. Whatever that X had, X was what? Horsepower. So horsepower data, minimum and between minimum and maximum, randomly it will bring 100 values. That random values are going to predict the PGs. Following? For random values, we are going to predict the MPGs. How do I put this? Remember this on pages here. It's very polynomial transform. It saves in space. Contains 100 numbers randomly between minimum of the horsepower and maximum of the horsepower, 100 values. These 100 values are here. Okay. Now I'm going to use these 100 values into the prediction. So this is again, we have to transform it. So X range, whatever is that, we transformed it to X range poly because we need a, this is going to give me list. I want it as numpy array. So this is that X range poly. Then we use this to predict. We have already built the model here. See, model.predict is already done. Where it is here. So we give this randomly generated as X value, and we want to see what the model is predicting now. This red color, plt.plot X range, comma, Y range predicted. X range, comma, Y range predicted. Let the color be red and let the label be polynomial fit. Red color, all these red color things are here, and name of the legend is polynomial. Okay. So, how many of you understood what I'm saying? How many of you didn't understand? Give me a 0. VTU students are good at biology. Okay. So there is one. So somebody said that Purnima J, ma'am, you said VTU students are very good at by hearting. You're saying that. So what happens if you go and by heart? You become a overfitted model on training data. So if you become an overfitted model on training data, real world, when the testing happens, that model won't perform well. So that's why we can't make people by heart. Okay. Even if eventually people become successful not based on what they by hearted, I think it's based on what they are able to understand. And by hearting, I believe in only by hearting essays. When in school, when we by hearted, when our teachers made us by heart everything, English poems and English comprehension, stories and everything. The reason why we are able to speak in English properly is because we got schooled very properly where we were supposed to by heart. So by hearting works when you're learning language so that you can capture those contexts. In logic, it won't, but hopefully we can change. We are all new generations now. We can change the system. We can put something else. So everybody understood why we are doing this. Again, watch the video. You'll eventually make sense of it. Not a problem. You will make sense of it. So X label, horsepower, Y label. So you'll see the X label and Y labels here. Okay. X label is horsepower, Y label is MPG. Then you all this, the decorations, and you see the fit is like this now. See something else, change the degree. You want to see a better fit, change this degree. Change this degree of freedom and run on. Doesn't matter now, I guess, because it's fitting. We were trying to build that, right? So now see, you see this, the curve overfitting. We are going towards overfitting. And you can also see the R squared value is 0.73. Reduce it to 0.74. Oh, the degree was less. It was able to do. Now see, even though you have polynomial equation, polynomial regression, you want to give more degrees of freedom. But when you give more degrees of freedom, some other dot is going to pull it like this, these outliers. So these are all outliers that can be removed. And you can see that these outliers are just that section of the normal distribution. So all the normally distributed values are here. 66% around in fact, it's like this, 66. These outliers are here. And this is what you want. If you remove the outliers, you can actually fit better. And do the needful. So that's what we are going to do here. Now let's quickly. So everyone's on. Give me a zero. Okay. Doubt about polytransform. Okay, doubts about polytransform. Is it easy to visualize two attribute data and examine some variables? If many attributes are there and one target attribute, I'm unable to visualize and access and multiple attributes. How linear or polynomial must be running for multiple dependent attributes and how to plot in x-axis? We can't plot it. Okay, you cannot plot something as complex as that. I think we had one example here in the morning. Yeah, you see, the maximum thing you can do is for a three-dimensional, you can look at it like this. Think of this as MPG, PG, and think of this as horsepower, and think of this as any other variable in terms of the acceleration. Okay, so how the acceleration, horsepower, and miles per gallon. What is the, so this is a three-dimensional field. It is a two-dimensional mesh. Okay. Now to answer that question more succinctly, we will tell you that have this. Okay. Let's say you have more. We can't visualize it. Okay, we can't. But can I reduce this? The full, yeah, of course it's here. So how do I reduce dimensions here? So to reduce the dimension, we use something called principal component analysis, which is also part of this. So I'll teach it tomorrow. Okay. Principal component analysis can reduce your dimensions. If it is 3, you can reduce it to 2. I'll show you how we can reduce it to 1 also. Take a line from the center and project it outside. This is a bad line. Okay. Line from the center and project it outside here. Okay. Now, whatever data was here, project this data onto this single line. All data. This also on here. This also onto this. One line is going to hold all the variation information of all other dimensions. Is making sense? One line, one equation is going to embody the relationship between all. So that is how the dimension gets reduced. And like this, there is one component. Like this, you can draw another in this direction and get all the projections done on this. These are called components. These are components. Now you rotate this, your actual dimension. You can only have these two components, and between that you can have. That's principal component analysis. Okay, we'll do it in depth, full extreme depth. We'll do it. Not a problem. We'll compute everything. But then the question is nice that you at least had that doubt that. And by the way, this whole shift from this Euclidean or Cartesian coordinate to linear algebraic combination. So what is going on here? What gets trapped here? We trap the linear combination of this x, the y here, and the z here. How is the linear combination? How many parts of x and how many parts of z makes a point on this projection? So how do you know how many parts? You develop a concept called unit vector and express that unit vector in terms of the eigens, and then you do something called singular value decomposition. Once the decomposition happens, you are now able to express everything in terms of certain matrix. Transforms, some are just summations, u, v, and some other u transform. So we'll learn about this probably. Okay. So once this transformation happens, your linear transformation happens. And all the image processing problems are all linearly transformed. This is linear algebra. You linearize the entire algebra of the relationships. That is how we think about it. Okay. So interesting, right? How many of you feel that it is like super crazy interesting? It is, right? All the attributes that you only one hypothesis. So for all the attributes, there must be only one hypothesis. Yeah. In fact, the end goal, Sahil Shah sir has asked for all the attributes, there must be only one hypothesis line. Oh, how do I answer that? Hypothesis is only one. But if there are many attributes, can I reduce those attributes to lower dimensions without losing information? Because our biggest asset in the data is variance. Capture the variance, you've captured the model. But can we reduce the dimension of the data without losing that variance? The question. That is what PCA helps you to do. So bring down that multi-dimensional data into 3 or 4 components. Maximum you could bring it to 2 components. You can, right? But when you bring it down to 2 components, you will see that how much variance loss is happening with you. So I'll explain. I mean, this is not the date for it. Tomorrow we'll understand everything. Okay, because we'll dedicate the time for it. But similarly, but it's also going to help us in terms of what we're going to learn next. So let's close this. Let's come back to our code. So your polynomial regression is over. Watch the video again. You'll get better.